Right, what have we got? We've got this nice thing here where if you differentiate the moment generating function with respect to t and evaluate it at t equals 0, evaluate it at t equals 0 here, you get the expectation. Now I'm just going to remind you of something that we did like, minutes ago. If f of x, just some function, equals a0 plus a1 x1 plus a2 x squared plus and so on, then f differentiated n times at 0 is equal to n factorial a to the n. We did that a long time ago because as you differentiate, remember the power comes down by 1. Each time you differentiate, you reduce that power by 1. And so if you've got an x to the n term, you differentiate it, it goes n x to the n minus 1, and then n minus 1 x n minus 2, and so on, yeah? So when you get down to 0, which is the one we're interested in, you've got n factorial there. So what am I trying to do? Can't remember now. Oh yeah, we've got this moment generating function business. What I'm going to do is to differentiate it n times. So I'll write it out all again. So we've got m sub x moment generating function of t equals the expectation. It doesn't hurt to write it out every single time. Expectation of e to the tx, which equals the integral from minus infinity to infinity of e to the tx p sub x of x dx. Sweet. Expand that exponential, so it's 1 plus t plus tx even, plus t squared x squared over 2 factorial plus t cubed x cubed over 3 factorial plus blah 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 plus see if I can scroll this over here, yep, t to the n x to the n over n factorial plus dot dot, we haven't finished yet, plus all of that times probability density function of x, and we're integrating the whole thing. Remember we've got an integral sign here from minus infinity to plus infinity with that's respect to x, and that's my moment generating function m sub x of t. Now I'm just going to differentiate it n times. Differentiate with respect to t, not x, t. And remember I said it was a bit cheeky. It's a bit cheeky because what I'm doing is I want to differentiate outside the integral sign, and I'm gonna differentiate the thing inside the integral sign. So I'm swapping over my order of differentiation and integration. And if I wanted to, nobody does, but if I wanted to, I could spend weeks talking about that. Okay, so what happens? Drawing a veil and moving swiftly on. So I'm going to say d by dt to the power n, where this is a kind of differentiation with respect to t operator of m sub x of t, and I'm going to evaluate this at t equals 0. Well, that's equal to the integral from minus infinity to infinity, that's x going over there, of, well, what's happening here? Let's have a look at this. I'm going to differentiate n times. Yeah, I'm going to differentiate n times where n is some fixed integer. So with respect to t, so what's going to happen is, look, this t to the n goes to t to the power n minus 1, then it goes to n minus 2, n minus 3, n minus 4, and because I'm doing it exactly exactly n times, this coefficient, this power of this term here will have a power of 0. It'll move all the way back to there, and look, that n factorial that comes because we've got t to the n, n minus 1, n minus 2, n minus 3, that factorial is going to cancel out this one here. How about that? So it's going to be equal to the integral of stuff that's vanished. When you differentiate anything else, if it's a t to the power n minus 1, when you differentiate it n times, it's going to vanish. It's just constant, and you differentiate it and it drops off the end. Once you differentiate a constant, it goes to 0. So there's this kind of conveyor belt going this way. It's going boing, 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 and then when it gets to the constant term, it stops, because you differentiate a constant, you get 0 because it's constant. Okay, so what have we got? And the n factorial's cancelled as well. From this term here, the n factorial's cancelled. So we've got of x to the n plus t times, well, it's t times the next one in the series. The one here, I guess the next one is going to be t to the n plus 1 x n plus 1 over n factorial. But I couldn't care less what that is, because I'm evaluating this beast here. This beast I'm evaluating at t equals 0. It says it there, look, it says it there. So it's here, the exponential term, it's x to the n plus t times some stuff, which I don't care about. I don't care what's in there, because I'm evaluating at t equals 0, so it drops out. Plus t squared times some other stuff. I could figure it out if I wanted. Plus other stuff. I don't care what that is. Times the probability density px of x dx. Sweet as. Okay, so now I'm going to use the fact that I'm just working it out at t equals 0, and we have got equal to the integral from minus infinity to infinity of x to the n plus nothing, because all these t's we're looking at t equals 0, so that's nothing, 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 times p sub x of x dx. Fantastic. So that equals the expectation of x to the power n. So here we have it. Here we've got moment generating functions in all their glory. We've got the moment generating function x of t differentiated n times, evaluated at t equals 0, equals the nth moment, the expectation of random variable x. I've put the bracket in the wrong place. Get rid of that if I can. Get rid of that. Go back to writing mode. Boink. Oh dear. Let's try that again. N. There. That's it. That's it. That's it. Isn't that clever? Isn't that really neat? So we'll start talking about moment generating functions. They've got another couple of nice properties too, which I'll talk about in the next one. Okay, done. Stop and take a break. My voice is cracking up.